Today, in this video, we'll learn about work energy theorem. The work energy theorem states that the net work done on an object is equal to the change in the object's kinetic energy. And this is shown in the equation below, where the net work done is equal to our final kinetic energy minus our initial kinetic energy. Or, kinetic energy can be broken into 1/2 times the mass of our final velocity squared minus 1/2 the mass of our initial velocity squared. So we see that the change in kinetic energy is strictly due to the object changing its velocity, since the mass of the object doesn't change. So if a positive net work is done, our kinetic energy is increasing, meaning our final kinetic energy is larger than our initial kinetic energy. If we have a negative net work, it means our kinetic energy is decreasing, and therefore our initial kinetic energy must be larger than our final kinetic energy. And if our net work is 0, must mean that our final initial velocity remained constant. When using the work energy theorem, there are two types of forces that we must account for. A force is considered to be a conservative force if the work done against them can be easily covered. Or we can say the energy is conserved and not lost. An example of this would be in our figure to the right, a man picks up the box. As he picks up the box, he's putting work to lift the box. At the top of the maximum height, the box has a potential energy. When the man drops the box, however, the potential energy will decrease. However, this energy will be transformed into kinetic energy. On the other hand, non-conservative forces is energy that is lost in a form that can't be easily recovered. These forces, for example, may be air resistance or surface friction. When applying it to the work energy theorem, we see that the net work is a sum of conservative forces and non-conservative forces. We see here, we have an example that states that a 70 kilogram base runner begins to slide into second base when he is moving at a speed of 4 meters per second. The coefficient of friction between his clothes and earth is 0.70. He slides so that his speed is 0 just as he reaches the base. And we're asked to find how much mechanical energy is lost due to friction acting on the runner. So first, if we summarize our information, we're given the mass of the runner to be 70 kilograms. The runner has an initial velocity of 4 meters per second and a final velocity of 0 meters per second, and that the coefficient of friction between his clothes and earth is 0.70. In order to find the amount of energy that is lost due to friction, we can apply our work energy theorem, which states that our net work is equal to our final kinetic energy minus our initial kinetic energy. So our net work will be equal to 1/2 our mass times our final velocity squared minus 1/2 the mass times our initial velocity squared. Since our final velocity is 0, our final kinetic energy will also be 0. And if we take 1/2 the mass of the runner, which is 70 kilograms, times our initial velocity of 4 meters per second, take it to the second power, we'll see that the work lost due to friction will be equivalent to a negative 560 joules of energy. And part B, we're asked how far does he slide. So we have found the work that's been lost due to friction. So we know the work from friction is also equivalent to the force of kinetic friction times our change in displacement. And since we have our coefficient of friction, we can solve for the force due to friction, and we know our work from part A, we can solve for our change in our displacement. We see that the force due to kinetic friction can be broken up into the coefficient of friction times our normal force, which happens to be mg. Since the friction force is in the opposite direction of the linear motion of the base runner, our angle will be cosine 180 degrees since it's in the opposite direction, times our change in our displacement. And since we're trying to solve for how far he slides, we can solve for our change in displacement, which will give us an final equation of work over our coefficient of friction times our mass times our gravity times the cosine of 180 degrees. And if we plug in the values we are given, we know our work is a negative 560 joules. Our coefficient of friction is 0.70 times our mass of the runner, which happens to be 70 kilograms, times our acceleration due to gravity, times cosine of 180 degrees. And when we calculate this out, we'll see that the runner will have slid a total displacement of 1.2 meters.